Hello, good afternoon, everyone. I am Somanna, and first I will introduce the today's topic. The title of the current topic is Mixed Signal Processing and its Application to AI Architecture. The entire topic consists of a number of sections. In the first section, we shall discuss about introduction to mixed signal processing, digital and analog signal processing, disadvantages and drawbacks, reconfigurable digital signal processing, and architecture. FPGA as a building block for digital reconfigurable architecture also. In the second section, we shall discuss in details number one, introduction to configurable analog circuits using switched capacitor, concept and architecture of field programmable analog array, FPAA, advantages and its limitations. In the third section, concept of AI, neural network, and machine learning, backpropagation network, how to train a NN and training algorithms, etc. And at the fourth section, analog digital AD processor, a new architecture for efficient implementation of AI algorithms and applications like image classifications. And today, our esteemed professor, Professor Amitabha Sinha sir, will deliver this session. Professor Amitabha Sinha sir is currently working as an advisor of a startup company, Aris Technologies Incorporation, Montreal, Canada, and engaged in the design and development of VLSI processor for AI applications. Professor Sinha was professor and director of School of Engineering and Technology, West Bengal University of Technology, Kolkata. He was a senior faculty member of the Department of Computer Science and Engineering, Bengal Engineering College, now Indian Institute of Engineering, Science and Technology, and Department of Computer Science and Engineering, BITS Pilani. And his areas of research include embedded system design, VLSI design, digital signal processing, processor architecture, system of chip design, etc. He was visiting faculty of Department of Computer Science and Engineering, Oakland University, USA, and was an expatriate faculty member of a premier Malaysian university, Mara Institute of Technology. Professor Sinha was the senior manager and DSP group head of Public Sector CMC Limited, R&D Center, Hyderabad, and was the vice president of R&D of HFCL, one of the leading telecommunication companies in the country. He has published more than 100 research papers in peer-reviewed international journals and conferences and co-authored 4 books published by Lab Lambert Publication, Germany. Professor Sinha had chaired a number of conferences, including IEEE, and delivered invited talks in India, USA, Singapore, China, Germany, Russia, Australia, and Hong Kong. Professor Sinha has supervised a number of PhD students and more than 100 MTech students. He was a member of advisory board electronics of Department of Science and Technology, Government of West Bengal, and was a member of Senate in BITS Pilani. Professor Sinha holds a doctorate degree in computer science and engineering from Indian Institute of Technology, Delhi. Professor Sinha is the fellow of the Institute of Engineers India and the recipient of Indian Leadership Award for Education Excellence from Indian Economic Development and Research Association, New Delhi, India in 2013. So, sir, please you can start with this session. Thank you.
Okay. Thank you very much. Is it coming now?
Yes, it's coming.
Yes, sir. Okay. So now, can I start now? Hello?
Yes, sir.
Yes, sir.
Yes, sir. Yes, sir.
Yeah.
Yes, sir. Start, sir.
Okay. So, good afternoon. The topic of discussion is mixed signal processing and its application to AI architecture. So before going into the details, let's try to understand why mixed signal. In fact, we know that the advantages of digitals are in terms of accuracy, flexibility, storage, etc. But all real-world signals are analog in nature. Means signal can be processed in analog signal processing system directly. So hence, there is no need to sampling the signals and then after sampling quantizations. So these things are not required for analog signal processing. So that's a great advantages. But for digital signal processing, all these steps have to be followed. However, in fact, digital and analog both have their own advantages and drawbacks. That, in fact, in minute details we'll be discussing. Now, what are the disadvantages of digital systems? As we discussed just now, like quantizations. After sampling, quantizations have to be done. And quantization means some error will be there, which is known as the quantizations error. And also the finite register length error. Because any analog signal, when it will be converted to digital, then it will be stored in some register. And the register size is finite. It could be 8-bit or 16-bit. It cannot be infinite. So there must be some limitation of the accuracy. The traditional analog systems usually had the disadvantages in terms of bandwidth, storage, accuracy, and also the flexibility. Like, our earlier concept was analog signals cannot be stored. They are not flexible. But these concepts are no longer valid today because of the advancement of technology. Of course, bandwidth is a problem because analog systems are exhibiting higher bandwidth. Digital systems are exhibiting higher bandwidth than analog today. And accuracy level, in any case, the digitals are always having higher accuracy compared to analog counterparts. The reason being, analog circuits are governed by resistors, capacitors, inductances, etc. And you cannot get the exact value of resistors or capacitance. Moreover, due to change in temperature, humidity, the value of the resistors get changed. As you know that RT equal to R0 into alpha T, 1 plus alpha T plus beta T squared, this formula we know. So depending on the temperature, the resistance also gets changed. So the signal level, what is expected at the output level, cannot be same because of the change in temperature or humidity. So definitely the accuracy level will fall. Signal to noise ratio will be increased. So these are the severe drawbacks of the analog signal processing. Now mixed signal processing is becoming popular as it leverages the advantages and drawbacks of both analog and digital signal processing. That's why these mixed signals are becoming so popular. We know that integrated circuits are generally classified as digital, analog, and mixed signal ICs. So digital ICs, the examples of digital ICs include microprocessors, memory chips, DSP processors, then CPLDs, FPGAs, whereas analog devices include operational amplifier, RF circuits, etc. Mixed signal IC devices that contain both digital and analog on the same circuits. They are in fact available on the same chip. That means in a same chip, digital and analog, both circuits are available. Typical example is today the advanced DSP processors in a same chip that includes DSP processor, memory, A to D converter, D to A converter. Now, this category of chips has grown dramatically with the increased use of 5G cell phones and other portable technology. So because of the advance of communication technology, where we require analog and digital both on the same chip, these devices are becoming very popular. Typical example is the communication receiver transmitter. We know that for receiver or transmitter in the front end, RF circuitry is a must, and RF circuitry is analog circuitry. So continuous time analog signals are converted to digital signals for further processing in digital domain. So ADC is such a mixed signal IC to do that job. ADCs are basically combination of analog and digital circuits. If we know the architecture of analog to digital converter, we'll see that it consists of both analog and digital circuits. So mixed signal ICs are essential components for FM tuners in digital products such as media players, which have digital amplifiers. Okay. Any signal such as FM can be digitized using a very basic analog to digital converter, and the smallest and most energy efficient of these would be in the form of mixed signal ICs. For an example, today software defined radio, cognitive radio, they have become very, very popular, and chips are also being available, where in the same chip the communication devices front end like RF circuitry and then the digital circuitry, these are available on the same device. So these are some examples which give you the range of mixed signal products. Just now I told you that DSP processors are available in a chip where ADC, DAC, memory, controllers all are available in the same chip. So the examples are there. So here in fact for 5G handsets, 3G handsets, this analog digital are available on the same chip. And recently, field programmable analog arrays have made it possible to design flexible analog circuits where FPGA and FPAA, combining them on a same chip, a lot of advanced devices can be made possible. So mixed signal circuits and products, if we just look at the products, mixed signal products are really created entirely in the analog or digital domain these days, as I told. Many new improved applications have now been made possible due to innovative integrations of firmware ranging on DSPs or microprocessors. What is firmware? Now, do you have any idea about firmware? Anybody can tell what is firmware?
So combination of software and hardware.
No, combination of software and hardware is not firmware. Firmware, exactly what is that?
Well, basically, we are writing some codes which have some protocols, and that will be obeyed by the communication in between two hardware.
No, basically these are the bit streams. Firmwares are basically bit streams. For an example, for many, you just take the example of FPGA. FPGA is what? Is a programmable hardware device, isn't a hardware device which can be programmed. So this program, you write a program using hardware description language like your VSDL or Verilog. Now, for a fixed applications, what you could do after writing the code in Verilog or VSDL, you will compile it when everything is okay. After testing verifications, then you will get the bit streams. And these bit streams will be downloaded onto the FPGA so that the FPGA can behave like a particular hardware. These bit streams are basically the firmware. Understand?
Yes, sir.
Yes, sir.
Yes, sir.
Similarly, if you consider a computer system based on conventional processor, conventional CPU. Now here, when you switch on the computer, first a boot program will be there, isn't it?
Yes, sir.
But before that, first a BIOS will take the control. And what is BIOS? Basic input output systems. It's a program stored permanently in the memory of the computer in some area using EEPROM or EEPROM. And this firmware is nothing but the machine code of the program. So understand what is firmware?
Yes, sir.
Yes, sir. Understood, sir.
Yes, sir.
Now, by changing the firmware, which is basically the bit level software. So firmware is nothing but the bit level software. Can't you say that? Which is
Yes, sir.
very close
Yes,
to the
sir.
machine code. The entire analog circuitry can be changed. So for an example, an analog circuit, let's say FPGA, the counterpart in analog circuit is FPAA. FPAA stands for what? Field Programmable Analog Array. So what is the beauty of that? Like FPGA, by changing the program, you can change the entire hardware. For example, you have an FPGA chip. You have designed some, let's say some controller. So you first have written the code in Verilog or VSDL, rather in high-level description language. And after testing verifications of this code, you have downloaded the bitstream onto the FPGA. So FPGA will behave like that particular hardware. Like using FPGA, you can design a CPU also. Okay, and CPU will have instruction sets and all. And depending on the CPU, you have written the code, and that code you have compiled, and the bitstream have been downloaded onto FPGA. So FPGA will become that particular CPU. Now, if you want to change that CPU, what you have to do? You have to change the code. So it is highly flexible. Similarly, field programmable analog array, they can also be programmed by analog description language. And if you want to change the hardware circuitry, easily you can do that by changing the code. That means by changing the firmware, you can easily change the characteristics of the hardware. Now, one may ask the questions, why? What are the advantages? The flexibility?
Sir, sorry, sir. I have a question, sir. Sir,
Yes.
sir, in FPGA, we are downloading bitstream. In FPA, what we are downloading?
That's the bitstream in different form.
Same bit.
I've not yet discussed the FPA. When we'll discuss FPA, we'll see that,
Okay,
of course, that is
okay.
also bitstream, but in a different form. Okay?
Okay, okay.
Okay. But what is my intention of saying is that, what is the advantage of that? Why do we require flexibility? Now, one thing I'm telling you, the most important thing in engineering and technology is not only to solve a problem only, to find out what is the problem. And particularly for the engineers, that I'm telling you from my own experience as working as a practicing engineers in different industry and also in the academic institutions. Today, throughout the world, there's a big competition. It's a global competitions. We very often call the global market. And in fact, in these competitions, who will survive? Those companies will be able to survive who can come to the market very first and with newer products, and who will be able to translate the need of the customers, actual need of the customers, to the reality. So that means the thing is that, let's say in the research lab, you are only doing research for years and years. That will not help you. Your research has to be tangible and it has to translate the market need, the market demand. And I'm telling you, today, let's say you have purchased one mobile handset, maybe 5G handset. Okay, and you may be proud of that because your friends may not be having that. But you will find in 3 or 4 months' time, somebody might have come up with a better one, and the cost may be less. You may be frustrated then. So because this is because of what? Because of tremendous technological development and competition. And in this competition, that company will survive properly who can come to the market very fast. And coming to the market very fast, how it is possible? It is possible by keeping the hardware same if you can change the product by changing the software, because it takes less amount of time. So if you go for the hardware cycle, it takes a long time. I'm not discussing all this cycle today, but starting from your design to a product, hardware product, it takes long time. Instead of that, if you develop the hardware once, of course, for a given cycle of time, every product has its own lifespan, maybe 2 years or 3 years, depending on the economy of the country. Also, because here in our country, maybe in fact a mobile handset, very good quality mobile handset, we can afford to have it with us for 5 years or maybe more than that. But in a developed nation, it may be 2 years or 3 years. And overall life cycle, overall life of the product may be 5 or 6 years. So it is very important that to use the hardware resource a number of times. So designing hardware once, if we develop software and can change the product, of course in the upward directions, then that will be too much customer friendly. So that is why the flexibility is very important. Dear students, why I'm telling these things, very often when you ask this question to the students, what is the requirement of flexibility? All the answers which come from most of the students are theoretical. And most of the industries, they are in a position to listen from you what is the reality, in fact, what is the industry oriented. And this is the reason, the flexibility. And that's why today, whenever any digital or analog devices are being designed, we just look at the flexibility, how flexible it is. Okay. And that's why the mixed signal processing with the high level of flexibility, that is the need of the hours. Now, any questions on the flexibility? Hello?
No, sir.
No, sir.
Yeah. You can interrupt.
Hello.
Me.
Hello.
Hello. Yes.
Sir, actually, we have seen that the speed of an FPGA is slower than the speed of an ASIC. So, are we compromising the speed for the flexibility in this case?
Look, ASIC is definitely, it is true that the speed of ASICs are faster than that. But whenever you design any system, then only speed is not the factor. There are many other issues, isn't it? And when we think of the hardware speed, then that speed can also be managed by using parallel processing. Can't we? So if we make the algorithm in such a fashion, such that within the device, within the system consists of what? Whenever you are designing any system consists of some subsystems. Can't we say that? And subsystems are nothing but the interconnections. A system is nothing but the interconnection of the subsystems. So if we refine our algorithms in such a fashion that many of these things can be done parallelly, many of the subsystems can be done concurrently, then we can manage these things. So that is the innovation, that is the research. But for that, the flexibility is more important than a fixed device, because ASICs, the basic problem of the ASIC, I'm telling you. Now, at the end of the day, for a company, the product has to be sold in the market. And there is a tremendous risk also in the market. Because today, whatever you have developed, within 3-4 months, you might be finding that your competitor has come to the market with a better product. Then, let's say 1 million products you have already developed. and entire thing have to be thrown on the dustbin. Instead of that, if little bit of speed can be sacrificed, but my market orientation is better, which one you will like? And today, because of the technological advancement, the speed between ASIC and FPGA is very less. It's not that much. And that can be managed by developing the better algorithm. So today, earlier, only we used to think only about the speed. But today, it's a combination of mathematics and engineering. In the hardware, in one hand, we are thinking of how to get a better speed. At the same time, we are thinking how to enhance the speed of the algorithm by refining the algorithm into the parallel sectors such that many of the units can be done in parallel. So this is a trade-off between these. But definitely flexibility, we cannot compromise with that. That's the most important thing from the business point of view. Is it okay?
Yes, sir. Yes, sir.
Yes, sir.
One thing in this context, just I'm telling you, again, I'm telling you from the experience and handling. Look, as far as the engineering technology is concerned, all the institutes you will find, whether it is IIT or any small college, you won't find much of a difference. The basic difference you will find, the orientation, how a student can orient himself or herself according to the need of the market orientations. That is the thing. That's why you will find most of the IIT students, they are successful in the business. And in 90% in the business sectors, they are dominating as a business administrator. So that is very important. So that's why I suggest, you also will have to orient. Theoretical is okay. You have to study. Without that, you can't do anything. But along with these things, you have to orient yourself with the current market trend. And that is very important. Now, difference in analog and digital design. That is also very important. When you are designing, we are thinking of mixed signal processing circuits, designing the mixed signal circuits. We must have to understand what are the differences, what are the underlying differences between analog circuits and digital circuits. And that means that will translate to the changes in analog design and digital design. Analog engineers spent a large amount of time on layout, grounding, calculating noise effect and signal to noise ratio, gain bandwidth, designing noise removal or filter circuits. So a lot of efforts have to be put for designing analog circuits. Truly speaking, analog circuit designs are much tougher and much more challenging compared to digital circuit design. And there are many cases where there are no substitutes to analog circuits, like RF circuit just now I told you. Okay, but digital circuits, since they are in the level of 0 and 1 mostly, designing digital circuits are relatively simpler. I won't say that is simple. There are many issues. Digital circuit doesn't mean only 0 and 1, because delay issues are also very important issue that has to be considered. That's why when many of you, when you write the code in hardware description language, after that you find that it's not working properly because timing violations, which apparently when you are writing in the logic level, you cannot check those things. But if you are an experienced engineer and if your electronics is very strong, then you'll be able to understand why these timing violations are coming. I'm giving a very simple example. For designing a processor, say program counter at T1 cycle, the contents of program counter will go to memory address register. So logically, you make program counter enable and output enable, and memory address register input enable. If you do that, then automatically your contents of program counter will go to memory address register. Theoretically is okay, but practically, let me tell you, exactly the time at which your output of the program counter is getting enabled, it will take some time because it's signal which will be traversing from program counter to memory address register. Some amount of time will be required, maybe microsecond, but still it is a time. And if it was on at that time, but by the time when the signal has entered, it's not enabled, so false data will be entered. So that's why this timing has to be calculated very carefully. Otherwise, so that's why I'm saying theoretical design and exact the things what happen, that has to be taken care of. So that means, that's why I'm telling you, so digital design doesn't mean only 0 and 1. These things have to be taken care of. That's why delay, hazard I have already, in fact, some time back, perhaps when I used to take your class, I discussed about hazard, the problem of hazard, by giving a very small example. Say you have an AND gate. One input is X, another input is X bar. What will be the output of the AND gate?
Sir, 0, sir.
Apparently. But let's say if
Yes,
I give a pulse, at the input X, then there will be a glitch for a time. Why? Let's say when initially it was 1 at the upper input, and lower input it was what? 0. Listen.
Yes,
Yes,
sir.
sir.
So let's say the upper input was 0. Then the lower input was 1.
Yes, sir.
Let's say the upper input has been made 0 to 1. Then upper input is 1. And lower input, still it will be 1, because to go from 1 to 0, it will take some time. Couldn't get it.
Yes, sir.
Yes, sir.
Yes, sir. Yes, sir.
So that means for a small time, both the upper input and lower input both will be 1. Is it not?
Yes, sir.
Yes, sir.
Yes, sir.
Which is basically the delay of the NOT gate.
Yes, sir.
So that means that it is called a glitch. Is it desirable?
No, sir.
No, sir.
It's not desirable. So that means it is a noise. So how do you understand? So when you have a very complex circuitry, you have to take care of these things. Anytime this can, when just now some of you asked me speed, that means more the speed will be there. That means this delay and all, a minute delay will create a lot of problem in the circuitry. So that
Yes,
means
sir.
designing a circuit doesn't mean only in the logical level. You have to consider all these things. Circuit delay, timing. So a good design engineer will consider all these aspects. So these are also required in digital. Still, I would say that analog circuit designs are more challenging compared to digital circuit design. Now, up to that, do you have any questions? You can clarify.
No, sir, I have no questions.
Okay. So now, so we understand, briefly we understood the difference between analog, digital and mixed signal circuits. Okay. And also we understood some advantages and drawbacks of. Now we'll discuss in details. So need of digital signal processing. Initially we had analog signal processing. Traditionally, we have been using the analog circuits. So digital circuits are relatively newer compared to analog. But why? One thing, the analog circuits are less expensive compared to digital. To address these questions, let's first have a look at the drawbacks of the analog signal processing. And then how these drawbacks can be overcome by digital signal processing. Okay, if we can get these things, we'll be able to address this question, why digital signal processing? Now, let's have a look at the drawbacks of the continuous time or analog signal processing. Very often these continuous time signal processings and analog signal processings are synonyms. However, there are discrete analog also, I'm telling you. Okay. This is not signal processing class, so I don't want to go in details of that, but discrete analog means when analog signals are sampled, after sampling, we don't get the digital signal. Still, after sampling, it is an analog signal. So it is called discrete analog because after a finite interval t, we get the signals, isn't it? Let's see, I have got some slides. If we just look at this, yeah. Now, you just look at this diagram, the bottom diagram and the right-hand sides. The analog signals are sampled at a regular interval capital T. So these are the sample signals. But sample signals are what? Still analog or digital?
Analog.
Analog, sir.
Still analog. So we can call them discrete analog. Okay.
Yes, sir.
So this is continuous analog, we can say. Then we have discrete analog, and then this discrete analog will be converted into digital signal by quantizations. So that's why whenever we convert an analog signal to digital signal, what are the steps? Sampling, quantizations, and coding. Okay.
Yes, sir.
Okay. So anyway, let's come back to our original things. So the drawbacks of the analog signal processing systems are inaccuracy, as you understand why they are inaccurate. Because analog circuits, these are very common questions for interview. Why they are not that accurate like digital? The reason being, the analog circuits consist of resistors, capacitor, inductors. These are called the passive devices. And you cannot get exact value of resistor or capacitors, first of all. Secondly, they can change subject to temperature variations or humidity or pressure or anything. So because of these physical parameters violations, their values get changed. Then output signals will also be changed. And as a matter of fact, signal to noise ratio will be decreased. So whatever varies from your exact values, that is the noise. So this is the inaccuracy associated with the analog signals. Inflexibility, because analog signals are not programmable. That was a myth earlier. But recently, this has been overcome by programmable analog devices. Until recently, the programmable analog devices were not available. And whatever available in the market, even some 15, 20 years back, they were a very low bandwidth. But in recent times, NRDG, a semiconductor company, they have come up with flexible analog circuits. That means they can be changed by changing the program. Okay. And these high-level programming languages are also available for analog circuits. And another drawback is the bandwidth. So bandwidths of the analog circuits are relatively lower compared to the currently available digital circuits. And advantage of digital circuits, of course, many of you must be knowing all this. So digital signals can convey information with less noise, less distortions and interferences. Thus, they are more accurate. Because in digital circuits, once you get the signal level 1 or 0, then their values don't depend on your any resistance or capacitance or this kind of things. Okay. So as signal processing algorithms can be altered by changing the program in a digital signal processing systems. They are flexible. For example, any algorithm for a given applications, let's say, these algorithms can be converted to a discrete things, like any continuous signals can be converted to discrete signals. And for an example, any differential equations, say output input relations can be described by differential equations. Say you have an LCR circuit. All of you have studied LCR circuit. Let's say input is a voltage signal and output, let's say you want to take the output across resistors or capacitor, anything. So there is a relations, and that relations can be described by Kirchhoff's voltage current equations given by differential equations, because Vt, if Vt is the input voltage equal to I into R for resistance, the voltage across resistors, plus L di dt, voltage across the inductors, plus 1 by C integration of I dt. So it is nothing but a differential equations. Now, how this differential equation will be solved by a digital computer? So this differential equation need to be converted to a difference equation. Okay.
Yes, sir.
Difference equation is nothing but the discrete version of the continuous differential equations. And once it is a discrete form, it is in the algebraic form totally. And this can be done easily by a digital computer, which is the DSP processor. So basically your filter algorithms or Fourier transforms algorithms, which are in digital signal processing, can be developed by these algorithms. Now, if you want to change it, easily just change the program. So that's why they're flexible. That means keeping the same hardware, just by changing the program, you are converting one product to another product. So that is the beauty of the digital signal processor. And that's why today, in today's world, software is so popular. The whole idea is you design a hardware. Of course, you put effort, you put R&D effort for maximizing the potential of the hardware. And from that, you extract the potential of that by developing a better software. Because for software, you don't need any raw materials. Raw material is your brain. And that is the reason in today's world why everything is being thought of in terms of software. But definitely one thing, you won't be able to develop software unless your domain knowledge is very strong. And for that, you need the domain knowledge of that subject and the mathematics. No, the flexibility in designing digital system offers faster time to market and economy. This is very, very important. Why flexibility? It's not that for academic exercise. The most important factor is time to market will be very fast. So in this global competition, the company which will be able to come to the market at a faster time with a better product will be able to survive. So that is the competition, and this competition is giving birth of the talented engineers. More and more research and development is being going on. If you see today, the top level companies like Qualcomm or your Intel, Motorola, the total competition is who can come up with the better product. If you go through the manuals, you just take the example of FPGA, manuals of Actel or your Intel, Xilinx, of course, Intel has taken Xilinx today. You will find that in every 3 months, 4 months, newer products are coming. Now, digital signal processing is safer because digital informations are often easily encrypted and compressed. And one thing is very important in today's technological world, how to keep your design encrypted. Otherwise, somebody else might take it. How to make it, your copyright should be done properly so that nobody can copy it. And for that, encryption is very important. And especially for security in the communication, encryption, decryptions are very important. Even for designing the software-defined radio, where, let's say, a commander is giving some instructions or commands to his soldiers. And in between, if somebody can decrypt it, can get all these things, the informations might be leaked. So that's why periodically, randomly, these informations are encrypted and then decrypted in that way. So here digital systems are very, very fruitful for doing this kind of jobs. And another thing, digital signals, another advantage is they can be stored on any semiconductor memory or other medias. So earlier, in fact, the analog devices didn't have that kind of facilities, but today analog memories have come in the market and commercially they are available. So they can also be stored. And analog memory earlier, the sequential memories were there, like many of you must have seen the tape recorder.
Yes, sir.
In the tape recorder, how the informations are stored, the music or anything, they're recorded on the magnetic tape.
Sir, magnetic.
Tape. So these are also kind of memory, but these are sequential memory. Okay, but today semiconductor memory, these are available. Okay, semiconductor analog memory. And disadvantages of the digital signal. So these all are the advantages of the digital signals, whatever we have discussed so far. There are some drawbacks as well. You should know. Sampling may cause loss of information because when you are sampling, then it won't be exactly the same like the signal. Whatever small it is, some amount of error will be there. So some information is lost. So in fact, quantization errors are there after from sample signals when you are quantizing. And round of errors will be there because after all, you cannot have infinite bits of registers. Some finite register length will be there. So some informations will be truncated. Then processor speed is limited. This is not true today, in fact. Okay. Systems and processings are more complex in digital compared to analog. A higher bandwidth is required for data communications in comparison to analog transmissions of an equivalent information. It's true. Because here bits, say 16 bit of information, that means 16 pulses will be required. So the bandwidth requirement for communications will be higher, which is not true for analog. And details about the digital signal processing, I've already discussed, this accuracy level. Now here an example is there. This analog signals by digital signal. Just a minute. You just wait a bit. I'm coming in a minute.
Caprio? Hello? Caprio? Hello?
হ্যালো হ্যালো
ক্যাপ্রিও রেকর্ডিং চালু আছে?
হ্যাঁ 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 স্যার
ঠিক আছে, ওকে।
Hello.
হ্যাঁ ইয়েস স্যার
Yeah. So, can you hear me now?
ইয়েস স্যার
Yes, sir. Yes, sir.
Flexibility already we have discussed, and the advantages of flexibility also have discussed. Errors, quantization error, finite register length errors. These are the errors in digital signal processing. So today is, I think, okay, advantages of analog signal processing. So analog components are cost effective. So they are less costly. They are attractive to many applications due to significant reductions in power dissipations, areas, and high speed. For many applications where high level of accuracies are not required and required less cost, analog devices are suitable. And these applications include artificial intelligence, machine vision, machine learning, deep learning, convolution neural network, etc. So there, analog circuits are becoming very popular. As on date, there is no substitute to analog signal processing circuits for RF signal processing, as I have mentioned earlier. So why do we need flexible analog ICs? Or really do we require? As we have discussed that faster design, development, and product ready time, this is required. So whether it's analog or digital, flexibility is very important because of the faster time to market economy. And due to rapid change of features in electronic systems, provision of changing the circuit by firmware has become an essential feature. So basically, the change will be done by changing the firmware. Firmware means the software in the bit level, which will be stored permanently. And if permanently in the sense like whenever it will be stored for FPGA or FPAA or CPLD, the characteristics of the hardware will be changed. So this in turn requires flexibility or reconfigurability. And it also helps for faster prototyping. Because for developing the actual product, prototype is a must. Prototype is a kind of experiments which enables the designer whether your concept is already correct or wrong. It's called proof of concept. So for proof of concept, prototype is a very important thing. And there also you need the flexibility because you have to change, you have to alter unless you can reach at a final design. So that's all for section A. Next we'll be discussing in the section B. If you have any questions, you please go ahead.
Sir, I have a question regarding the FPAA. Normally, any analog circuit we design using cadence like the schematic of the analog circuit. But in case of FPAA, what we done? Like in FPGA, we use Verilog or VHDL.
No,
Oh,
is an extension of Verilog. This is a different programming language that is there. I don't know whether you have that. I send it to Shovik, I think, some informations. We'll discuss these things in the later. When we'll go for FPA, then we'll understand it. Okay?
okay, sir. Thank
Okay,
you.
it is not like VSD. It is a different thing. You can define resistors, you can define capacitors, this kind of things are there.
Okay.
Sir, I have one query.
Yes, please.
Sir, you have talked about the bandwidth, analog signal bandwidth. So regarding the, we are here actually using the sampled signals in analog processing. So up to which frequency we can process this analog signal? What about the high frequency analog signals?
No, high frequency. In fact, the RF signals, if you see the range of the RF signals, then you will understand.
So then, sir, what will be the
Because
sampling rate and what will be the ADC?
today's sampling rate, I'm telling you, today's sampling
Yeah.
rate is not only for a
Yes.
single sampler. You can use a multiple sampler. For an example, let me tell you a simple example.
Okay.
Say you have an A to D converter. Okay. Let's assume that you
Okay.
have a fastest A to D converter, which is available in the market, which samples after, say, every T unit of time. Understand?
Yes,
It
sir.
samples after every T unit of time. This is the, let's say, the fastest possible sampler. But
Okay.
let's say your bandwidth is such that you have to sample at T by 4 at that rate.
Okay.
Then what you will do? You use 4
Yes.
A to D. You use 4 A to D converter. Okay.
Okay.
First, you give the signal to the first one, to all of them, the same signal. The start
Okay.
signal. First one you give the start signal. Then after T by 4 time, the second A to D converter you give the start signal. Then the third one, then the fourth one. Okay. Then the first one,
Okay.
after T unit of time, will give the first results, the sample value.
Okay.
The second one,
Okay.
from here after T by 4 unit, it will give the third
Okay.
after T by 4. So then you using a multiplexer, high speed multiplexers, you take them one after one. So what is the effective sampling
Okay.
rate after every T by 4 unit? Is it not?
Yes, sir. Yes, sir. Sir, okay, sir. Can I ask something, sir? Sir,
So
what about then that? Oh,
so we
that
have
means, sir, we have to use the mask which will um, select one line by T by 4 timing,
yeah
then next one by
yeah
that way, and that will be controlled by the processor, sir.
that can be controlled by any hardware circuits. I'm telling you, these are
Okay.
design concepts. In that way,
Okay.
even with a lower sampling rate, you can make a higher sample. Here is it not basically a concurrent processing of analog
Yes,
circuits?
sir. Yes, sir.
So these are the techniques these are used now. From a
Okay.
single
Then
device, always don't expect that it will give you the extreme, because ultimately your speed will be limited by the speed of the velocity of light. You cannot reach that. So that's why what we are doing, whenever we are thinking of enhancing the speed, we are in fact devising many other techniques to enhance the speed of the things.
so suppose the frequency bandwidth of the signal is 25 gigahertz, then sampling rate must be the twice of that.
That's okay.
Then that means
That is all right.
okay.
What I said is something else. I said that he used multiple number of these samplers and enhance the speed.
Okay. So
Okay.
then my question is then how the processor can be handled, how the processor can
Why
handle this,
why the processor comes here in the picture? Here you are
sir,
thinking
because
in terms of sampling.
okay.
In terms of
Yes.
sampling, you're thinking. Always you don't have to think in terms of only processor. And
Okay.
today, the processor doesn't mean that it will be working sequentially. FPGA is also a kind of processor, but the concept of FPGA processing is totally different than a von Neumann processor. Understand my point?
Okay. Uh,
Processing
so
means,
ultimately the demarks will get signals within T4 time.
yeah, because
T by 4 time.
DMAX complexity is
Uh,
much less. If the complexity is less, any hardware, any device, then your speed will be higher.
okay. Okay.
Okay.
Okay. Okay. Thank you, sir.
In fact, these concepts we developed when Professor P.K. Nandi and myself, sometime in late 80s in B College, we developed it. Because we got a consultancy from a company for getting a faster, and that time your 0808 A to D converter was not able to give that speed, and I used some 80808 and got a speed 8 times faster than that. We just designed it on a board PCB and we made it.
Oh, so that means you have beat the processor speed also. Yeah.
Yeah, we enhanced the speed of the A to D converter.
Yeah. Yes.
So today there are so many techniques are there by which we enhance the speed. So always you don't have to think only for one. Okay, this is the bandwidth of that. My ultimate target is how to solve a given problem, and what is the best mechanism that can be used for solving a given problem. That is more important. So your mindset should be open. You should not be stuck
Yes.
to only one point.
Okay.
Okay. For an example, I am telling
Yes, sir. Yes.
you, many of us might be thinking how very high speed clock can be developed. Very high speed. For an example, you have a processor. You are designing a very high speed processor. For that, you need a very high speed clock.
Yes, sir.
A gigahertz clock, if you just try to design outside the chip, then there will be some electromagnetic interference.
Yes, sir.
A lot of noise will be there. Now,
Yes, sir.
it can be done by using a low frequency clock to generate a higher frequency clock. You know how I'm telling you. Say, you take a clock, relatively lower frequency. Low frequency doesn't mean I'm saying 20 hertz or 30 hertz. Frequency relatively lower. Okay?
Okay.
Outside the CPU. Inside the CPU, let's say, is a clock 50 megahertz. I want to make a gigahertz. What will do? It is a periodic signal, isn't it?
Yes.
If it's
Yes,
a pulse, it's a periodic signal. Now, any
Yes, sir.
periodic signal, according to Fourier series, can be converted into infinite number of harmonics,
Yes, sir.
isn't it? So, if the fundamental frequency f, then within that there are 2f, 3f, 4f, 5f kind of
Yes,
signals are
sir.
there. Of
Yes.
course, their heights will be slightly lower, but these
Yes.
signals will be
Amplitude will be.
there. Yeah, but signals will be there. So, what I can do
Yes, sir.
inside the chip, I can design a bandpass filter.
Yes,
So,
sir.
my basic frequency is f, and I will, let's say, I will extract 5f signal or 10f signal, but of course the
Yes,
level will
sir.
be very low. Then amplify it.
Mm.
You are getting higher frequency signal, isn't it?
Yes, sir. Yes, yes, yes. Yes, sir. Thank you, sir, very much. But this query is coming, another query, sir. Actually, when we are increasing the frequency, then the amplitude is decreasing for higher frequency. That means we have to design a, very good bandpass filter also to
Yeah,
select that frequency,
yeah.
and
That
also
will
we
happen.
need a very
That is
we need the amplifier also.
that is of course required.
Yes. Yes.
So, like you are solving the problem in a different way altogether. You are extracting the high frequency signal from a low frequency signal.
Mm,
That is the beauty of the Fourier
mm,
series. So, your
mm.
mathematical ability, your physics, knowledge of electronics, all these things have to work simultaneously, isn't it? For getting a better solution.
Yes, sir.
And that's what
Yes, sir.
later on, in other day I will share with you. When I was in Auckland University, I had the opportunity to work in the automobile company. Like we had to go for some 1 month training and all in an automobile company, because in USA, what happens, all the faculties, they have to work in the industry for some time, okay, in every year. So there we are finding, in fact, even the mechanical engineer, how beautifully in collaborations with the electronics engineers, they are finding out some solutions for their own applications in the automobile. So, okay, so that's all for today.
Thank you very much, sir.
Sir, Shamunna will conclude the session.
Okay.
Thank you, sir, for this wonderful session. We learned a lot about the product development and the newer trends in the industry and FPGA and FPAA. Thank you very much, sir, for this wonderful session. And we will again, this session will be happen in the next Thursday from 3 p.m. to 4 p.m. Thank you very much, sir, for this session.
Okay, thank you very much. Okay, so can I leave now?
Yes, sir. Yes, sir.
Yes, sir. Yes.
Okay, thank you.